So this is geometry lesson 4.5, reflections over intersecting lines. So in lesson 4.4, we did reflections over parallel lines, and we saw what happened. And now we're going to do it over intersecting lines. So the reflection image of a reflection image of a figure over two intersecting lines, so not parallel but intersecting, is a rotation image of the original figure. So remember, when we reflected over two parallel lines, we created a translation, and the special theorem we looked at said that the distance of the translation was double the amount of the distance between the parallel lines. That was 4,4. So today we're going to look at, well, when I reflect over two intersecting lines, it creates a rotation, and there is a special measurement of that rotation based on the two lines, and that's what we're going to look at. So for today, the definition of a rotation is going to be the composite of two reflections over intersecting lines. Composite meaning more than one. We're going to reflect over two lines that intersect and create a rotation. Now this first line just explains that the intersection of the two lines is going to be the center of the rotation. So remember, every rotation has a center. A lot of the times when we looked at them on a graph, the center was just the origin, 0, 0, and everything's rotating around that. And so our rotations, the center of the rotation, is going to be the intersection of the two lines. Two lines are crossing, we're reflecting over them. The spot that they cross is actually the center of the rotation that occurs. Now, because each reflection in the rotation preserves angle measure, betweenness, collinearity, and distance. Remember, we can remember that A, B, C, D. So does the rotation. So we know that reflections preserve these things. When you flip something over a line, the angles don't change, betweenness doesn't change, collinearity doesn't change, and distance doesn't change. So in these rotations, all of those will still be preserved because we're just doing a reflection twice. And since we are actually doing two reflections, then orientation is also preserved, which was true in 4.4 in a translation. And again, the reason is because I'm flipping something when I reflect it. And if I just do it once, orientation now is not preserved. I've flipped it over. But when I do two reflections, it ends up flipping back over, and now the orientation is back where you started. So that's why orientation will be preserved in these. Okay, so looking at just basic rotations, just to remember how we measure them. So this rotation is from XYZ, the starting triangle, and I rotated it this way around the center A. So in today's work, when we get to our intersecting lines, that point that it is rotating around, that will be the point that the two lines cross. That will be the center of the rotation. Now in this specific one, notice I went clockwise. And when you rotate clockwise, the rotation, the magnitude of the rotation is given as a negative number, as you can see. If I go counterclockwise, I express it as a positive. So this is already all drawn out for you. So clearly this is the measurement, the magnitude of the rotation. But notice how it's being measured. If these two shapes were given to you without this measurement here, if you had the center, you can take any one of the points on the original pre-image, draw a line to the center of the rotation, and then draw a line to the corresponding point. So notice I have y in the image of y. So each one draws a line to the center of the rotation, and then you just measure that angle. And it would be true for any of these points. If I went from Z to A, and then from the image of Z to A and measured that, it would also be 102 degrees. X to A to X would also be 102 degrees. So a line was drawn from Y to A to the image of Y, and that measurement there is 102 degrees, and that's how we measure a rotation. Okay, that's just a quick review of rotations there. So now for today, we're going to look at what happens when we reflect over two lines that are crossing, not parallel, but intersecting. What's the measurement of that rotation? And how many degrees is that going to be based on the angles that these lines are making here? So the two reflection theorem for rotation says, I'm going to read it and then I'll explain it to you. If line M intersects L and the rotation over, remember we read this way, over L and then M, has a center at the point of that intersection of M and L, the magnitude is twice the measure of an angle formed by these lines in the direction from M to L. So the magnitude of the rotation, so Notice I went from Q to the image of Q to the second image of Q. That's the full rotation, so this full measurement right there. It's saying that it's twice the measure of the angle formed by the lines. So the angle formed by the lines is right here. So if I know this degree measurement from the picture, all right, then I can double that degree measure, and that is the degree of this rotation. Now let's talk about why that's true. So when I do my first reflection from Q to the image of Q, so I'm just reflecting Q over line L. This measurement, how far Q is away from that line, is the same on both sides. We know that direct measurement, if I measured it from Q to line L to the image of Q, those distances are going to be the same. Well, if you think about it, this should make sense. If those distances are the same, then the angle created to go to both of them should be the same. And so they will be. So we're going to call this X and we're going to call this X. I have flipped Q over line L. The angle created on both sides is the same because Q and the image of Q are both the same distance away. And then the same thing is going to happen when I flip it again from Q, the image of Q, to the second image of Q over line M. It's going to end up on the same distance away from line M on both sides, and it's going to create the same angle on both sides. And so my total angle here, angle of rotation, for my two reflections, the total rotation that I've done here is x plus y plus y. That's the whole rotation from the original to the second image. So we can simplify that as 2x plus 2y, which we talked about in the last one. We can rewrite that as 2 times x plus y, because if I redistribute, I'm going to get 2x plus 2y. So that's the total angle of rotation here. And the angle of the intersecting lines, if you look at the picture, is just x plus y. You've got the x here and you've got the y here. And so the angle of rotation is going to be twice the amount of x plus y, 2 times x plus y. So it's always going to be double. So if I know what this angle measurement is, I can determine the degrees of rotation of my figure. So let's take a look at some of these. On to the back. All right, so example number 2 here. The picture is given to you. We have a rotation of triangle ABC. Here's the original over line M. So here's line M. It flipped over that. They're not showing that one. And then it flipped again over line N, and that gives us the second image of ABC, which is given to us. So the middle one, the original reflection over line M, is not pictured, just the final result of the second reflection. So we started over here at ABC. We flipped over M because it comes first, and then they flipped it over N. So B would have ended up down here somewhere when you flipped it over M, and then it flipped over N, and now it's here. Okay, C, now this one, you almost look at it and you're like, it almost looks like C wasn't reflected. But remember, C, you got to go 90 degrees here. So C actually would have ended up over here when you reflected it over M. And then when you reflect it over N, it ends up on this side. Same thing with A. 90 degrees past M, then 90 degrees past N. All right, so if I went from the center Z and I connected to B, and then I connected to the image of B, I'm trying to figure out what's the degree measure of that. That wasn't a great line there. So that looks like a pretty big angle, right? So that's more than 90 degrees. And so since this 70 degrees here is vertical to this 70 degrees here, I know that they are equal because of those vertical angles. And if you go back to our theorem, the angle measurement between those two intersecting lines as you move across them is 70 degrees, then my full angle measurement out this way is going to be double that. So it's going to be 140 degrees, which is 70 times 2. This is going to be 140 degrees. And that makes sense, right? We're not a full 180. A full 180 would put us over here, straight line. Okay, so, but definitely more than 90. 90 would be down here. So 140 degrees makes sense. And which way did we rotate? We rotated this direction, which is counterclockwise. So this is going to be positive 140 degrees. So it actually is pretty simple. You just take a look at what was the angle on the inside of these two lines that I flipped this over, and you just double it. That's it. All right, so for example 3, I want to talk about how direction does matter here, though. So there's no difficult math. You're just timesing by 2 to figure this stuff out. But you do also have to take notice of where's the angle, what's my vertical angles, and which direction these are going. So let's describe the center and measure of an angle to determine the magnitude of the rotation. We're going to go over Q, and then we're going to go over E. We're going to do it for 2 different shapes. And I'm going to talk about how this measurement is actually going to be different. So let's actually start with this one. So we're going to start with the pentagon. If I flipped it over, oh, I'm sorry, we're going over E, and then we're going over Q. So if I flip it over E, I'm going down here somewhere, and then I flip it over Q, and I'm going over here somewhere. Okay, so that's going to be a pretty big, if this goes here and then over here, think about that angle, and that's going to be pretty big. That's looking like at least 180 degrees, something like that. It might even be more, it might be a little less. But if I flip over this and over here, that's 90 would be down here. So yeah, that's pretty big. And so I have to measure this angle right here because that's the middle of this composite reflection. The reason I'm kind of going slow over this is because remember, I have angles in here as well, and they are not 114 degrees. And so if I'm flipping over that space, which I might be doing when I flip this one, that degree measurement is going to be different. All right, so for this one though, I went down here and over here. So over E, over Q. This is the measurement between E and Q that I'm going over. And so I'm going to double that to find my measurement. Now, these are verticals, so this is also 114 degrees. And so if I double that 114 degrees, the rotation that this is going to go about for these 2 reflections is 228 degrees. So more than 180. So 180 would be right through M. So like let's say here, 180 would be directly over here. So we know it's actually going to end up above that. When I flip this, it's going to rotate all the way over here past 180, 228 degrees. All right, so that seems pretty standard. That's like the same thing I've done the last couple examples. But let's take a look at this one. The reason I put this example on here is because sometimes we're going a different direction. And this one also, just to go back to it for a second, we were going counterclockwise, so we would express that as a positive 228 degrees. But this one now, if we're going over E this way, and then over Q, now if I took this right through M, I'm actually going to end up over here. This one's going to end up over here somewhere, and then when I flip it over Q, it's going to go to here. So that's going to be less than 180 degrees if you think about it. This line through M, if after all of my flipping and rotations, I ended up over here, that would be 180 degrees. But if I take this and I flip it over E, 90 degrees, it's going to be somewhere over here. And then when I flip it over Q, it's going this way. And so my final shape's going to be over here, less than 180 degrees away. And so how am I going to find that measurement? So since I'm going over E this way and then over Q this way, the angle measurement that I'm looking at to determine the total rotation is this one. So over E, over Q, this degree measurement is what's going to get doubled. So how do I find this one? If that's 114, we know that these are supplementary, right? We've got these two being equal. These two are going to be equal to each other, but together with the 114, they're going to equal 180. So if I do 180 minus 114, because they're a linear pair, that's 66. So this angle in here is 66 degrees. This angle in here is 66 degrees. And if you just take a look at it, it's less than 90. That makes sense, 66. And so this is going to be half of what the rotation is. All I got to do is double this 66 degrees to figure out what that is. So 66 times 2. We'll write it out so when you go back to your notes, you can see it. 66 times 2 is going to be 132. And so this rotation, it's going to go this direction. That is now clockwise. So it's going to be a negative rotation of 132 degrees. Again, less than 180. 180 would put it over here. But since we're reflecting over E and then over Q, it's going to be a total rotation around center M of less than 180. So it's going to be 132 degrees. And again, negative because we are going clockwise.